Add 0.1 to 0.2 and you do not get 0.3. Print the result to 20 decimal places and there it is, 0.3000, a string of zeros, and then a 4 right down at the 17th digit. So the comparison against 0.3 is false, and the puts never runs. This is not a bug in C, or in your compiler, or in your processor. 0.1 has no exact representation in binary, for exactly the same reason that 1/3 has no exact representation in decimal. You can write 0.3333 for as long as you like and never quite arrive. Binary has the same problem with any fraction whose denominator is not a power of 2, and 1/10 is one of them. So the moment you type 0.1, you are already holding a value that is very slightly not 0.1, and the error, tiny as it is, survives the addition and shows up in the comparison. Every language with hardware floating point does this. C just does not hide it from you. So never compare floating point values with double equals. Instead, ask whether they are close enough, and be explicit about what close means. The first form is an absolute tolerance. Take the difference. Take its absolute value with favs from math.h and see whether it is smaller than some small epsilon. That works well when your numbers are all of a similar, modest size. It fails badly when they are not. If A and B are both around 10 to the 20th, they cannot possibly differ by less than a billionth. Because the gap between adjacent representable doubles up there is far larger than that. Hence the second form, a relative tolerance, scale epsilon by the magnitude of the values being compared. So the test asks whether they agree to a certain number of significant digits rather than to a certain absolute amount. Which one you want depends on your problem, and there is no universal epsilon. Anyone who tells you the answer is always dBL_epsilon has not thought about it. Pick a tolerance that means something in the units you are working in. 2 more realities of IEEE 754, the standard your hardware implements. Dividing by 0 in floating point does not crash your program. Integer division by 0 does, but this does not. It gives you infinity, a real value you can carry around, compare, and print. And 0 divided by 0 gives you nar_n, not a number, which is what the hardware produces when the answer is genuinely undefined. Nar_n has a property that catches everybody. It compares unequal to everything, including itself. So nar_n equals nar_n is false, which means the test on that slide prints 0, and it also means x not equal to x is a perfectly valid, if cryptic, way of asking whether x is nar_n. Do not write it that way. Use the functions in math.h, isnin, isinf, and isfinit, which say what they mean and work regardless of what the optimizer has been told about your floating point model. And be aware that nar_n silently propagates. One nar_n anywhere in a long calculation turns the entire result into nar_n, which is actually the friendly behavior, because it means the corruption cannot hide. And as with the integer types, you do not have to look any of this up, the header knows. Float.h gives you the properties of the floating point types on the platform you are compiling for. dBL_max is the largest finite double, around 1.8 times 10 to the 308th. dBL_min is the smallest positive normal value, which is not the smallest positive value. There are smaller subnormal ones below it with reduced precision. And dBL_epsilon is the one people misunderstand most often. It is the gap between 1.0 and the very next representable double. It is not a good general-purpose tolerance, because the gap between representable values scales with magnitude. Up near 1,000,000 the spacing is 1,000,000 times wider. What it is good for is expressing a relative tolerance in units of the last digit, as in a few times dBL_epsilon times the magnitude. Each of these has a float counterpart with an FLT prefix, and a long double one with an LDBL prefix, following the same pattern.